Mathematics. What's the first thing that popped up in your head? A subject that is super confusing and difficult, or a universal tool that transcends all languages and could be used to discover the secrets of the universe? Hi, I'm Talia,
And I'm Joshua.
and welcome to our podcast, The Uncommon Senses, where we discuss the nature of knowledge and on how we know what we claim to know. Welcome to our special series of interviews where we discuss different areas of knowledge with our guests. Today we have John Lee, who is a university student from the University of Warwick, pursuing a major in applied mathematics. So, John, tell us a little bit more about your major and perhaps share a bit more on your university life at Warwick. Like, what specifically are you studying, the program you're enrolled into, and living abroad and living in Warwick?
Sure. So, hello everyone. I'm John, and I'm currently a math and stats student at the University of Warwick. So, in the first year, I was initially enrolled in a course called Morse, which is a joint degree. It's short for math, operational research, statistics, and economics. And as I've been attending my lectures, as I've been learning more, I found that my interest really lies in math and stats. So now I've sort of specialized or narrowed down my degree into math and stats. And it's mainly a lot of probability. And in year one, it's more of proofs and introduction to like the field of math and stats. And yeah, it's pretty interesting. So I'm excited to be on the podcast today to share what I know and maybe see what you guys know.
Oh no. That's quite a concern. Well, yeah, thanks for your sharing. So, without further ado, let's jump into some knowledge questions on mathematics. And
Sure.
again, most of these questions here are obtained from the website IB Mastery. So, a lot of thanks to them. So, John, some people may critique math to be a rather rigid discipline, given that quite often there is only one set of answers to a problem. So, what would you say to counter that? Or would you go as far as to say we should embrace its rigidity? Could you share a little bit about what's appealing about mathematics to you?
Well, when you say that mathematics is very rigid, I think what you're referring to is the rigor that is required. I think one of the big jumps you get from secondary school math to uni math is everything is very rigorous in university. Like we do a lot of proofs which need to be like it needs to be accurate and precise. And I think that's necessary. And for some people that might be daunting. That's probably why they don't like mathematics. But I feel like that's also why the people who do it enjoy mathematics. It's fun. It's challenging and we embrace the rigor. I would use the word rigor instead of rigidity here.
Ah, I see. So when you talk about, the accuracy and precision, would you say that all statements in math are either true or false? Or could there be like a middle ground or perhaps two contradictory correct statements?
Well, okay. So let me introduce the idea of a proposition. So a mathematical proposition is something which is by definition either true or false. And uh, that's just how it is. Uh, the truth of a statement is based on a set of axioms, which are they're generally agreed upon. But maybe later today, I'll give you a few examples where people do not agree on a set of axioms, and maybe that's where the discrepancy arises. But normally, um, mathematics is a discipline where you get one correct answer and we try to make it as accurate as possible. Yes.
Ah, so do you think this leaves much room for ambiguity?
Well, I think one, I think ambiguity. We try to eliminate ambiguity when we do maths, and well, maybe I'm still a first year. Maybe I still haven't got to maybe the most abstract concepts, and maybe I haven't got to like uh research. But at this stage, I feel like ambiguity is more of it's undesirable when we work with maths.
So when we say in mathematics, we try to narrow down on the ambiguity. We try to like make it as accurate as possible. Do you think that everything in math is certain in this sense? Do you think math is certain? So as an answer, that can the answer prevail through time? Can a theory, a concept prevail through time, or is it like it's always changing according to perhaps like paradigm shifts or like
Oh, okay.
changing logic?
Right. Good. Okay.
Yeah.
So, yeah, what I was trying to say is, uh, the fact that it has to be rigorous makes it so that it's susceptible to logical fallacies,
Mhm.
and we are uncertain whether our answer is actually accurate. Most of the time, we just like let the logical fallacies slip, and then we leave them unrecognized. And what you've been talking about paradigm shifts, well, maybe it will happen in the future, but um, I feel like most of is math is established in a way such that the most basic axioms are commonly agreed upon, and I feel like that won't change in the short term, and therefore any knowledge that is built upon these axioms will stay relevant for quite a period of time.
So you're saying that there's certain parts, like fundamental parts of maths, that are perhaps more unchanging or like less susceptible to changes, while
Yeah.
other parts that may be more that may change through time.
I feel like math is a discipline where knowledge doesn't really change, but we accumulate more and more knowledge. Like from one proposition, we find connections between different concepts and ideas, and we develop new ones, and that's how knowledge in math is produced and grows, I guess.
I see. But what happens if, let's say, the accumulation of knowledge is contradictory to prior knowledge?
Well, when a contradiction arises, we first of all try and understand why the contradiction exists, and we try to resolve it in several ways, whether the proof itself, the theorem itself is flawed, or whether it's because the axiom itself is not commonly agreed upon. I feel like another thing is the word paradox in math is sometimes misleading for people who don't understand what it is, because uh, there are sometimes paradoxes arise because they're counterintuitive, but they still agree with each other. So like it makes sense logically, and I feel like that's something people should know.
I see. And I think much of our discussion now has been surrounding knowledge, and logic, as you've mentioned. So, on another note, you've mentioned how, it's a common misconception that mathematics is purely logical.
Mhm.
So, in what way does perhaps personal beliefs or emotions or something that's more subjective place in this discipline?
Okay, so you mentioned how important logic and reasoning is. Instead of emotion and what was the other one?
Like personal beliefs.
Personal beliefs. In terms of a way of knowing, I would like to talk about intuition. So, if you don't mind, I'll give you guys a few math questions and I'll demonstrate
Okay.
how this
Oh, no.
works.
Okay.
So, first question, very easy. So, to make this accurate, I have a function from R to R, and the first function, f of x, is cosine of x. How would you differentiate that? What's the derivative of the function?
Negative sine x.
Good. So it's a very basic example, and here I think you've used memory more than logic,
Yeah.
right? I don't think every time you
Right.
differentiate cosine of x, you use logic and reasoning because it's something you've done, and so you use your memory. Okay, so next one.
I have no memory of that.
You have no memory?
I'm sorry, math teachers from secondary school.
Okay. So the next one, oh, you've got your computer open, so if you want to use like Wolfram Alpha or anything,
Okay.
feel free. The next function I've got is the natural log of cosine of x. So now, how are you going to do it? You don't have to compute the answer, but how are you going to approach this question? Maybe tell you?
What?
I would
Okay.
not approach this question in
Yeah.
the first place.
I guess like a chain rule or something,
Right,
like the
good.
natural.
Good, exactly.
Okay, the
So
end.
that's the intuition because you see that it's a
Oh.
composition of functions. So
Yeah.
your intuition is to go to the chain rule. And I would say there's less logic and reasoning here and more intuition here.
Hmm.
Mhm.
Okay. So the third one, it's slightly harder, but what if I take the natural log of the natural log of cosine x? How are you going to approach this question? It's very similar to the last one. How are you going to approach this question?
Should I just Chain
Chain
it
rule-
again.
Chain it again, right? Okay, so Joshua,
Oh,
do you
okay.
mind? So if you get Wolfram Alpha open now,
Alright.
or any
Wolfram Alpha.
yeah,
Oh,
or
okay.
symbol app, anything,
Okay.
you can try type in this. Well, I can type it in for you. If this is too long, just edit this part.
I think I'll edit this out because, like,
Yeah, but
clearly I've forgotten everything.
yeah. So okay, Wolfram Alpha tells us that
Ooh.
the derivative is the negative of tan x over the natural log of cosine x. Okay. So
Mm,
here, I think if I give you enough time, if you do the chain rule like twice, you can get this
Right.
answer, right?
yeah. Yeah.
So this is our intuition. But what I want to get to is this answer is wrong. This answer is completely wrong.
Mm-hmm.
Even Wolfram Alpha is wrong. Because now our intuition tells us, oh, it's again a composition of functions, so we should use the chain rule twice. But this is where logic and reasoning is used. Because I feel like in math, when we approach a question, we always start with intuition. Like intuition is the driving force of what we do. And
Yeah.
logic and reasoning is more of a way we backtrack. We check every step. Here, we've made a very, very big mistake. Talia, any idea? Any idea?
Why are you asking me?
Well,
There's like, I don't know.
okay, if you don't know, here to help. Look at the function log of cosine x.
Mm-hmm.
The chain rule is used correctly. Okay, we do actually get this answer if we use the chain rule, but we should not have used the chain rule in the first place because this function doesn't really exist. Cosine of x, well,
Right.
for the technical people, cosine of x ranges from -1 to
yeah.
1. Okay, and the domain of log is the positive real numbers.
Yeah.
So, okay, so for the first log of cosine x, we will only get, because cosine of x is smaller than 1, so log of cosine of x will always be negative. And so when we take the log
Right.
again, it's actually undefined.
Oh,
And therefore, this derivative does not actually exist. The function itself does not exist in the first place. So that's where logic and reasoning comes in. Okay.
right.
So I think this is one of the reasons why people think that intuition is probably a bad way of knowing in mathematics. They feel like, oh, this is when things go wrong, they blame intuition. But what I'm trying to get at is we always start with intuition. Just because intuition goes wrong, it does not mean that intuition is not important. If anything, I feel like intuition is more important because that's how we start. We use logic and reasoning to check every step and make sure things are accurate, things are rigorous, and it's intuition that got us here. And if intuition is wrong, we learn from this mistake, and next time we develop a better intuition. The next time, like when I've done enough examples, the first thing when I differentiate is to make sure the function is differentiable. So one way of putting this is intuition itself is not to blame. It's your bad intuition, which is causing. And when you do more math, when you do more problems, you'll develop a better intuition, and you'll probably make less mistakes. You still need logic and reasoning to make sure it's correct, but it all starts with intuition.
Yeah, that's very interesting. I feel like for, in high school education, quite often they also try to put this to the test. So sometimes they will design question explicitly where there is no correct answer or the answer does not exist. So I think, what they're trying to get is that they're trying to eliminate that, possibility that you got to the right answer by chance or by pure intuition. And they're trying to really look at, do you really understand the knowledge surrounding that particular question?
Exactly. So I feel like in secondary mathematics, we are taught more of how to compute these values. We're taught how to use the chain rule, like what the chain rule is. But we're not taught why the chain rule works and when we can use it. And I feel like that's one of the main differences.
Yeah.
Wow, you're making math more fun. Honestly.
Yeah.
Oh, okay. So, on the topic of intuition, so what do you think is the source of, intuition in math? So, what causes a person to think, oh, this is the right answer? What is intuition built on?
Well, I think there's a certain level of like memory, like pattern recognition that goes into it. Like I've done similar problems before, and I realized that a similar method would probably work here. Another thing is probably um just when we try to solve a problem, we try to establish a connection between like the question, the things we start with, and the answer that we want to build. And using like the theorems, the propositions that we know, we we try to build a bridge between the question and answer, and that's sort of our intuition. We start with that. We start with whatever pops up in our mind. Like most of the time, it's probably wrong. Like that's what I've learned.
Yes.
But it's there's also a bit of trial and error here, and the more you do it, then you're better at recognizing the right things to use in that case, and I think that's how your intuition gets better through time.
So you're saying that intuition is built on prior knowledge and experience on how much
Mostly.
you do.
Yes.
And as we know, when we're using memory, these are not, infallible sources of knowledge. Quite often they are distorted by emotions. They're distorted by perhaps your own negative bias towards the question, as you've mentioned. So perhaps when you're doing a question, you really want to arrive at one answer. So your brain already automatically geared towards that particular answer. So, in this sense, would you say that mathematics is subjective?
I wouldn't say it's subjective because more often than not, there is a correct answer out there. I think what you were pointing out there was that depending on our beliefs, which is our beliefs, what we know, we might approach the question differently, and sometimes that's what brings us to an incorrect answer. Like for example, when maybe we're trying to find the intersection point between two lines, okay? Our belief is that there is an intersection point, and then we assume that the intersection point exists and we try to solve for it. But sometimes it doesn't exist at all. And it's our belief that the intersection point exists. That's what causes us to make a mistake. And I wouldn't think it's subjective because that's objectively incorrect. Like when we verify the answer, I think most mathematicians, at least with more basic math problems like this, they are able to come up with a consensus that, oh, this answer is wrong or this answer is correct. As I've said, propositions, by definition, they're either true or false. Okay, Talia, you've probably done a few computer science.
Oh my God, don't even mention about it. Yeah.
Like, we can assign a truth value to propositions. But I think okay, I'm going to bring up an example where it's sort of subjective in the sense that different mathematicians have different beliefs. It's called the axiom of choice. Have you heard of it by any chance?
No.
Right. So I'm not gonna dive too deep into this. Like if you're interested, like you two or anyone listening right now, go online, search it up. But so to give you some context, how I got to know about the axiom of choice. So in term one, we had this module, sets of numbers, and we were dealing with infinity. So like the idea of infinity. So for example, well, countable infinities like the natural numbers, the real numbers are uncountable. Sorry, Joshua.
Yeah.
Yeah. So
This I remember.
One question that came up was, is it always possible to show that two different like cardinalities, infinite cardinalities, are either less than or equal to each other, or greater than or equal to each other? So, in other words, like, can we always compare two different infinities? Okay, and so here's the context, and with this comes the axiom of choice. The axiom of choice, it's well, in the simplest terms, it's basically saying that we can like there will always exist a choice function. Like if we were given an infinite number of sets, there's always a way to select a member from each of the sets. Okay. So, well, that's very technical, mathematical. I'm not going to dive too deep into it. But the discrepancy arises from the fact that for people who do set theory, this axiom could lead to some problems. A paradox, actually, which we briefly touched upon earlier. It's called the one such paradox is the Banach-Tarski paradox. Okay, again, you can look into that. It's a problem which arises because when we deal with infinity, the choice function is not always that easy. Like we don't know how to construct this choice function. For finite sets, like for us at the moment, the axiom of choice does not cause any problems, and that's why most people who don't do set theory or logic, we accept the axiom of choice. But for set theorists, they might choose not to accept the axiom of choice. And I think this is an interesting example where the set of axioms itself, it's not universal, it's not accepted by everyone, and that's something we never come across in like secondary school. And I think in cases like this, the truth, like that may be subjective. Depending on whether or not you accept the axiom of choice, you might come to different conclusions when you try to prove something. So
it really depends on which kind of beliefs you choose, or like perhaps like your expertise in that area.
Exactly.
So moving on, when we're talking about the subjectivity of truths and how in mathematics an answer could in one sense could be objective, in another sense could be subjective, depending on how you see it. So would you think mathematics is a human construct? So is it invented, or do you think mathematics is discovered in the sense that we use musings from nature, or perhaps when we come down to its core, it's down to objective natural truths?
I feel like there's no like absolute definite answer to this question, but personally, I'm more inclined to believe that mathematics is invented. It's invented by us in a way such that it agrees with more like most natural phenomena. For example, natural numbers. It's invented so that it's easy for us to count. Like they're sort of our counting numbers. Okay, do they exist? Like objectively, do they exist? Well, that's way too philosophical. Like I'm not going to go into that, but I believe we designed mathematics in such a way so that it's useful to us, and it agrees with most like physics, like science, the real world. It's just useful for us, and that's why we invented it this way.
But would you also say that there could be a potential weakness in that, in the sense that if it's invented, it'll be up to the whims of its inventor, in the sense that we can, easily change how we use or how we see mathematics?
Yeah, in some way, yes, but most of the axioms that we have agreed upon, they are the axioms we all use because they're useful, and unless like a major paradigm shift occurs, I believe that I don't see such a big change coming with math because we've been using it for so many years and it's worked. Okay, so maybe in more advanced fields, like more abstract math, or maybe some I don't know, technology, computer science and stuff. Maybe they have different needs, and therefore they might create some new math, which will be helpful to them. Like if we think about Isaac Newton back then, he didn't have a way to express his theorem, and that's why he invented calculus.
So he is to blame.
No, he's not to blame.
About our high school sufferings.
Oh, yeah. So I don't think that really changes what we already know. But as I've said, it's an accumulation of new knowledge, new stuff, and this way, it's not like oh, as an inventor, I just arbitrarily define stuff. I think a lot of thought goes into what they define, and I feel like it's more often than not, it's agreed by people, and that's how math is built.
Yeah, I completely agree with what you're saying. And I think that is the reason why we use math so much in our daily lives, from science to perhaps like polling, architecture, just all different types of fields. But but I think what we're talking about now is built on the assumption that all people who uses math uses it in a way that we want to advance human achievement. We're all in this quest to find out this objective truth in mathematics. But what will happen if like mathematics is used by someone with an ulterior motive? For example, they could truncate graphs to make it look more to make statistically insignificant differences look significant, or perhaps when we talk about math in financial statements, where we can have window dressing to make the sum seems more favorable, or perhaps math could even be, as we mentioned before, unintentionally altered, such as having this preconceived bias towards a certain answer and trying to work our way towards it. So in this sense, to what extent do you think math could describe or represent the real world? Or, at its core, do you think math is, dependable as a source of knowledge, given that there are so many, loopholes and weaknesses within?
Yeah, so what you've mentioned, like making fake statistics, fake data, making misleading conclusions from data, I feel like that is something we recognize, like it exists. And as I've said, it's nothing to do with math itself. It's how we use math. One thing, like I don't know where I've heard it, but someone once said like you can always prove any conclusion with any data as long as you don't you're not precise. Like you can create correlation conclusions from like two data points, and you can zoom in, like draw a nice line, and people will believe it. But that's not because math is flawed. That's because our understanding of math is flawed, and that's why um, data can be so manipulative, like in the media, because we always assume data is credible, but it's actually very easy to manipulate data. Like an easy example would be like you can have the bar chart. Okay, one is probably like shows 60%, the other is 62%. But you can zoom in, okay, you can set the baseline to be at, I don't know, 58%. And then the first bar would be only half as long as the second bar, and you would show like a massive difference when in truth it's only a 2% difference. Is that something wrong with math? I don't really think so. I think that's how math is presented by this person, whatever their agenda is. That's the problem lies there. And I feel like that's why it's important for people to learn math. Well, maybe not everyone's going to be a scientist or a mathematician. Like I recognize that like as if someone wants to be an artist at 13, it might be cruel to put them through like differentiation calculus throughout high school. But I still feel like mathematical education is important because that allows you to interpret math that's put in the real world accurately. And well, you asked like how dependable is math? Well, if we all learn math, it's going to be a lot more dependable, and we're going to be a lot less vulnerable to uh, misconceptions and misleading data in a sense.
That's very interesting. And as we know, all knowledge is limited, so it's impossible to say we gain a full knowledge of a particular field. So, how would you argue with someone who says, let's say, since our knowledge of mathematics is limited, could we just completely disregard some fundamental rules laid out for mathematics, since we could just say, oh, in the future someone could look deeper in it and perhaps disproves like prior knowledge or like the fundamentals that we have laid down today?
Well, it depends on who's asking this question. If it's an artist in secondary school asking this question so they don't have to do calculus, then I'm afraid calculus is probably going to be used for quite a while. It's useful, it's proven useful, and a lot of people use it, and helps with other fields, like generating new knowledge in other fields. It's useful. Maybe when it comes to like the most advanced research, like the abstract pure math, um, different people might have different theories, and learning one theory, like that theory could potentially be overruled by future theories. But does this mean that we don't have to learn them? I don't think so. I feel like every time we learn something new, it opens new doors. Like, as I've said, math is created in a ways such that it's useful for us. And maybe even though it might be overruled in the future, it has its use currently, and it's still useful for like knowledge development. So just keep learning. Just keep learning math.
Yeah, completely. I think, uncertainty should not be a reason of why we should disregard a field, as you said, that's so useful to our day-to-day life. So yeah, thank you for sharing with us the different kinds of theories related to maths and how despite its many flaws, math is still a very dependable source of knowledge for society or for individually. So moving on, we'll have Talia to discuss more practical questions related to maths and its applications.